Now, polynomials does get pretty heavy, okay? When we start talking about multiplicity of roots, and particularly now that you know about complex stuff and all that. But I need to take a few steps back, and I'm sort of not entirely sure where everyone is at on this. So even if you've seen this before, it's good to revise because sort of like, you know, building a structure, your foundations need to be really, really firm, okay? So we're thinking about division. We are going to move on to polynomial division, but where I want to start is just with numbers, okay? Because we understand numbers a lot better. So for instance, come in. Hello, you looking for something? Yeah, is there anything in there? It's all right. Thank you. Someone give me a 2-digit number.
3.
69. Please.
If you gotta do something, do it. You gotta do it yourself. Someone give me a 4-digit number. 6,000 what? 280. Alright, now, we can do this. Let's give it a go. Okay. 14 into 6, how many times? None. 14 into 62, how many times? 4 times 14? 56. So I'm left with 6, carry the 8. How many times? 4. Still 4? Still 4. Which gives you 56 again, which gives you 12, carry the 3. How many times? 8 times 14 is 112? Yes. So that gives us 11. Goes in no time, so that's what I've got. Okay. By the way, for bonus points, there are 3 numbers here, right? The 14, the 6,280, 448. They all have names. Which one's which? We know what the 3 names are, right? There's the divisor, there's the dividend, and the quotient. Okay, now, the easy way to remember this is that if you just write this out, they're in alphabetical order, okay? So you've got, what we did was 6,283 divided by 14, which is 448 with the remainder, right? So you've got, in order, dividend, divisor, quotient. It's just convenient that way. All right, now, we've just gone and worked out the quotient, but I want to write from this what we call the division transformation on the basis of this, okay? What this is saying is I can rephrase 6,283 as the divisor and the quotient together plus the remainder, yes? So I should say 14 times 448 plus the remainder. Okay, cool, good. This is fine. Now let's shift gears. Okay, let's go into polynomial division. Okay, I'll get rid of this guy. We don't need them working anymore. I just want this result. Okay. Okay, let's take similar kinds of numbers. Let's go. I'll make that 2. Let's take these guys. 6x plus 2x plus 8x. Let's just make it a -3 for the sake of it. All right, what do I do? You say, how many times does x go into 6x cubed? And the answer is 6x squared times whatever x may be. Now what? Multiply back, which gives me 6x cubed minus 2x squared. Sorry, 12x squared. What do I do with that? I subtract, which gives me 14. Bring down the 8. Okay, now what? 14x. Multiply back. 14x squared minus 28x, which gives me 36, subtract 3, how many times? 36, multiply back, 36x minus 72.
Sorry.
I promise I didn't do that on purpose. Seriously, that's really creepy. Okay, have you heard like those, those mathematical acts where they're like, oh, do all these things, and suddenly you get some magic number out of it. That's not what I intended, but anyway. All right, we did a division transformation for numbers. So how can I do this for the polynomial? What am I going to write? This is the original. No, this is the dividend. The dividend here is 6x cubed plus 2x squared plus 8x minus 3. Okay? So what's that equal to? X minus 2 times quotient. Okay? Yeah. Plus the remainder. Okay? Can't plan that kind of thing. Okay. Alright, so there you go, right? Now this division transformation is very important. It's vitally important for the remainder theorem and the factor theorem, okay? But just before I do show you the remainder and the factor theorem, right? Number one, hands up if you reckon you could quote for me the remainder and the factor theorem. Anyone? Okay, let's pull the bar a little lower. Who thinks they know what the remainder and the factor theorem are, even though they can't explain to anyone? Like, I think I might recommend. Yeah, okay, all right, hands down. We will get to that. But before I do that, I need to get you all on the same page in terms of never, ever having to do this polynomial long division anymore, at least if we have a monic linear factor. Okay, sorry, I should say monic linear divisor, because that's what you're usually going to get. Okay, so maybe you want to make a little subheading, which is synthetic division. Synthetic division. Now, I know some of you know how to do this, because I've seen the working out on your pages from when I gave you that test the other week, okay? But I know not all of you have seen it before, so I'm going to show it to you. Please note, synthetic division is primarily for monic linear divisors. It doesn't only work with that, but the advantages you see with synthetic division is that it is faster and simpler, but the versions of synthetic that work for other kinds of divisors, you start to lose some of that speed and simplicity. Okay? So instead we're just going to remember, we're going to learn the method for this, because that tends to be the most useful thing, okay, as you'll see shortly. So here's what I'm going to do. Do you notice, as we go down this long division, okay, the x's, the x terms, in some sense they don't matter, right? Because they follow a very predictable path no matter what the coefficients are. You're always going to get your x cubed here, your x squared here, your x's here, and your constants here, every single time without fail. That is, if you do your division properly, right? What's really important is the coefficients you get out of that process, okay? So the first thing we're going to do to save time is all we're going to write for the dividend is its coefficients. Okay, so let's write the coefficients. You're going to get 6, 2, 8, negative 3. Okay? Now, to help distinguish between this and long division, instead of doing the long division sign, we do the synthetic division sign, which is exactly the same but upside down. Okay? Radical, I know. Now what we're going to put over here, instead of this as the divisor, I'm going to put the 0 that corresponds to it. Now this is x minus 2. So the 0, or the root that you would get out of having a factor of x minus 2, is just 2. That's the number. Okay? Draw one more line. Right? Now remember I told you that we're going to only be considering monic linear factors. Okay? So if it's only monic, you know exactly what this number is going to be without having to do any calculations. Because you're always going to be dividing by 1, right? So you're always just simply going to get this number straight back. Does that make sense? The leading coefficient of the dividend will be the leading coefficient of the quotient every time if you're dividing by something monic. So here's my first step. All I have to do is write down the number 6. That's all. Okay? Now, apart from that step, I'm now going to do the step which iterates. It goes over and over and over again. Watch carefully. Follow with me. Okay? 6 times 2 is 12. I multiplied. Now I add. 2 plus 12 is 14. Okay? Multiply again. 14 times 2 is 28. Now I add, which gives me 36. 36 times 2 is 72. I multiplied. Now I add. There's 69. Okay? Now, just stay with me. What was the degree of the dividend? The degree of the dividend was degree 3. Now remember, I'm dividing by a linear divisor, so what would you expect the degree to be afterwards? 2. Okay? So remember we said the x's don't really matter. I can fill them in after. Watch. It's going to be 2, and then 1, and then a constant, and then a remainder. Okay? Was that faster? Yeah. Better believe it was faster, right? Not only is it faster, it's actually, once you get used to it, that is, it's less error prone, because as I go down, notice what I chose was the 0, which is the opposite of this number. Okay? So that's why here we were subtracting, but here I was not subtracting. I was adding. Now, addition and subtraction are the same thing, but believe it or not, most people's brains are better and faster at addition, even when they're exactly the same numbers. Okay? You're avoiding things like this where there are double negatives, if that makes sense. Okay?
Is that accepted?
It's absolutely accepted. It's absolutely accepted. Okay? Provided you set it out properly. Okay. All right. Now that's the way synthetic division works. Do you want me to do another example, or you're pretty content with that? Was that yes, another example, or yes, I'm content? Yes. You guys have no help at all. Okay. Another example, shall we? Okay. All right. Let's do some new numbers. Let's do. Yeah, sure. Let's go 2x to the 4 x All right. Now the great thing about synthetic is that the longer the quotient of the division, the more gains you get. So we're going to divide 2x to the 4 minus x squared plus 5x minus 3. We're going to divide by x plus 3. Okay, so what's the first thing that I do? It's the coefficients. The coefficients are what matter. Okay, so I go 2, and then immediately I notice there's no x cubed term. So another way of saying that is there are 0 x cubed terms. So I write the 0. Now, the rest of it proceeds minus 1, 5, negative 3. Okay? What will be the number I put here? It's the 0 that corresponds to this. So it'll be negative 3. Okay. You ready? The very first step, the one that doesn't repeat, is you just take the leading coefficient. You write it down. Okay? From there, I'm going to multiply, add, multiply, add, multiply, add. Okay, watch. Multiply, first time, gives me negative 6. Now I add. Okay? Multiply, gives me 18. Now I add. Multiply gives me negative 51. Now I, add. Is that right? Yes? Multiply, this is the worst number, well, I chose it. Negative 3 times 46, what's that? 120 plus 18, 138? Plus 120. Now I add them, which is 135, I guess. Okay, we started with degree 4, so I ought to end up with degree 3. 2x cubed minus 6x squared plus 17x minus 46, remainder 135. Now, if you want, you're more than welcome to test that out by long division. I'm going to go get on with other things, but I have confidence that that's right. Okay, we're doing exactly the same computations, just in a more efficient way, really. Okay. Now I said before that the way we learnt it only works with monic linear divisors, but I said that's kind of okay. Why? Why are monic linear divisors the ones you're going to be using over and over again? Why x plus 3s and x minus 2s? Why are they the ones that come up repeatedly? Okay, so it comes from the factor theorem. Okay, so I want us to look at this division transformation here. Okay, and I want us to think about it in general terms. Okay. So, that'll do. Okay, so now you can call this the remainder theorem. Okay. Now have a look at this thing here, right? We start with some polynomial. I'll call it P. Okay? And what we're saying is, I can phrase it in this particular way if I divide by something. Okay? So what we're dividing by, I'm just going to think about monic linear divisors. Okay? So generally speaking, they're of the form x minus a. And of course, a can be negative if we want to get x plus 3s and so on. Okay? Now, this other piece here, that was the result we got at the end. That was the quotient, right? So being that it's the quotient, I'm going to call it Q of x. And I don't know what it is because I don't know what P is. Then you get some remainder at the end, invariably, right? Unless it exactly divides, your remainder will be 0. Now have a look at this with me. If I can state this, which is kind of like this but in a general form, right? Therefore, if I substitute in that 0 that corresponds to the divisor, like this. This is a 0 that corresponds to a divisor. This is a 0 that corresponds to a divisor. If I sub it in, what happens? Well, this guy here will be a minus a. This will be q of a, whatever that happens to be. And then you have a remainder, right? But because I've chosen this specific value, because it's the 0 that corresponds to it, right? It turns this into 0. That's why we call it a 0, right? So therefore, this is just going to be your remainder, right? This is the remainder theorem, at least in algebra and equations. How could I word it? How could I word it? What does this result mean in relation to this? Okay. When dividing the original polynomial, right, by this monic linear divisor we just concocted, okay, you can instantly, without going through any of this fluff, right, you can work out this final number, the remainder, without going through any of the division at all, right? All you have to do is evaluate it at the 0 that corresponds to that, namely that. Shall we test that? How would I test it? We just did this division here, right? Okay, let's see how our brains are going. 2 times negative 3 to the 4 minus negative 3 squared plus 5 times negative 3 minus 3. Negative 3 to the 4. 81. Double it, 162. Yeah? Minus 9. Minus 15. Minus 3. That's minus 24, 27. Looks like it checks out to me. Okay? Which we ought to expect it to, right? Algebraically it makes sense. Okay? Now, the important version of the remainder theorem that we want is called, what's the special case? The factor theorem. Okay, we just did the remainder theorem. What is the factor theorem? Now that I've warmed you up, do you reckon you could tell me? Could we write something like this that would correspond to that specific time when we actually get a factor, not just a divisor and a remainder? Okay, now we want something to be 0. What do we want to be 0? Number 1, the remainder. which is this guy, P of A. So when P of A equals 0, what does that tell us about the original polynomial? X minus A, the factor that corresponds to this 0, sorry, the divisor, is a factor of your original. Okay? Because you test this out, you get a remainder of 0, sweet, it actually divides through. Okay? So in practice, what do? You get some rubbish polynomial like this. Okay? And you don't test 0. Why not? Why don't you test 0? Because there's a constant term, so you know it's not going to be a factor. They'd all have to have x's in it to be divisible by x, right? So you don't test x, you don't test 0, what do you test? 1. You test 1. And then if that doesn't work and you get a number, you test -1. And then you do 2 and -2. And you keep going about up to 3 and -3. Okay? And then at some point there you'll get a factor, right? There you can proceed just as we have here.